All right, we're going to prove that the general polynomial equation is insoluble by Ruffini radicals if n is at least 5. So what does that mean? It means that we cannot create such a tower where we iteratively add roots from the coefficients of f to get, where we iteratively add roots, right? So we iteratively add nth roots to go from one step to the next. Okay, so before we prove this, there's going to be one more thing I need to talk about. And that last thing before the proof is we're going to set delta to be the product of all pairwise differences in the indeterminates t1 through tn in order. So the guy on the left is always less than the guy on the right. This one is not symmetric. So for example, if n is 2, delta is just t1 minus t2. If n is 3, delta is going to be t1 minus t2, t1 minus t3, t2 minus t3. In particular, for the first one, if we swap 1 and 2, we get the negative, right? If I swap 1 and 2, I get t2 minus t1, which is negative delta. Similarly here, if I swap t1 and t2, these guys will interchange, but this one will introduce a negative sign. However, if we have an even permutation, you can't just swap 1 and 2, you have to do something else. So swapping, if you have an even permutation, it's a product of an even number of transpositions. And so every time you do one swap, you introduce a negative sign. But if you do an even number of swaps, you're going to introduce an even number of negative signs. So it's not symmetric, but it is sort of alternating group symmetric. And we have a word for this. We say AN invariant. The action of the symmetric group on this element delta, it will be plus or minus delta depending on if our element was from AN or not. Okay. All right. We're also going to set capital delta to be little delta squared, and this is called the discriminant. Okay. And since if we act on delta with any element sigma of the symmetric group, that's just acting on delta, little delta with the element of the symmetric group and then squaring that. When we act with the symmetric group, we're going to get plus or minus delta depending on how many sign changes we have. But if we square it, it doesn't matter if we have a positive or negative there, we just get delta squared, so we get delta back. So delta is a symmetric polynomial because we've gotten rid of that sign ambiguity. All right, so delta is the pairwise difference in the roots, the product of the pairwise differences in the roots in increasing order, and capital delta, the discriminant, is little delta squared. All right, let's prove it. Let's prove the theorem. So the general polynomial equation is insoluble by Ruffini radicals. Proof. Assume we have a tower as in the definition, where all the nj are prime. Okay. Let's look at the very first step. Where again, this is the symmetric polynomial, symmetric polynomials in the roots, and here is just the whole roots. All right, we're going to look at just that first step. So we know that K1 is obtained from K by adding in some alpha 1 such that alpha 1 to some prime, I'm going to say P1, is in K. Great. What can we do? Well, for any sigma in Sn, we know that sigma of alpha 1 to the p is going to be sigma of alpha. It's an automorphism, right? So behaves nice with respect to multiplication. Is going to be sigma of alpha 1 to the p1 rather. But alpha 1 to the p1 is in k, so it's invariant under sigma. It's fixed by sigma. So this is just alpha 1 to the p1. Okay, so what does that tell us? Well, sigma must send alpha 1 to a pth root of alpha 1 to the p1. Well, we know all the pth roots. Alpha 1 is one of them, and then we get one for all of the other p1th roots of unity. So sigma of alpha 1 must be some zeta to the j of sigma alpha 1, where zeta is e to the 2 pi I over p1. Okay? And j of sigma is just, it's just whatever the power is, right? There's not just the standard primitive unity, there's all powers of it. And depending on what sigma is, we might get a different power there. Okay, so in j of sigma is in between 0 and p minus 1. And actually, we have a map that sends a sigma to a pth root of unity. So actually, this defines a homomorphism. And we're not going to check it defines a homomorphism, but it defines a homomorphism. Sn to the set of all pth roots of unity, which is a group. It's isomorphic to Z mod P. Okay, and in fact, this homomorphism is it defines a homomorphism. I'm not going to say it's in general. Well, actually, it's going to be in general surjective. So we know that alpha 1 is not in K. We're adding in something honestly new. So sigma of alpha 1 actually, sorry, 1 second here, must not be equal to alpha 1 for some sigma, because if sigma actually fixed alpha 1, if all of the sigmas fixed alpha 1, then alpha 1 would be a symmetric expression in the roots, and therefore would be in K. But it's not in K because it's something new that we're adding in. Okay. All right. Okay, so this tells us then that this map is actually surjective. It's a surjective homomorphism. So Z mod P is a quotient of Sn. Well, this tells us that P has to be equal to 2, and the kernel is actually An by the lemma that we proved in the previous video. The only cyclic prime order quotients of Sn are when P is 2 and the kernel is An. Okay, so what do we know here? Well, elements of An then, when we see what they do to alpha 1, we just get alpha 1 back. So in this case, An fixes this alpha 1. Okay, so, all right, now what? Well, we claim that actually alpha 1 is in the field obtained by adding in this expression delta, the pairwise difference, the product of the pairwise differences of the roots in increasing subscript order. Well, let's prove that. Since P is equal to 2, we know that alpha 1 squared actually is in K. Not just alpha 1 to the P is in K. Well, that's true, but P is 2, so alpha 1 squared is in K. And so alpha 1 is a root of T squared minus alpha 1 squared. Okay. So this is the minimal polynomial of alpha 1 over K. Now, the images of alpha 1 under the Sn action Well, this is in K, so Sn has to just permute the roots, right? Because Sn leaves K alone. K is the symmetric expressions in the roots. So it has to leave this polynomial alone, and so it can only interchange the roots of it. It can't send the roots somewhere else. Okay? So the images of alpha 1 are plus or minus alpha 1. We know that alpha 1 is fixed by an, but not Sn. So there exists sigma in Sn satisfies this, so some permutation satisfies sigma of alpha 1 is negative alpha 1. All right, then what? Well, then sigma of delta alpha 1 is negative alpha 1 is delta alpha 1 for the elements that negate the alpha 1, and for the elements that negate alpha 1. Good. And so what this tells us is that this element delta alpha 1 is, well, first of all, it's fixed by an, but it's also fixed by the guys that negate them. So it's actually fixed by Sn. So delta alpha 1 actually belongs to K. All right. So what does that mean then? Well, then delta alpha over delta, if I have access to delta, that belongs to K join delta, because delta is there, delta alpha is in K, but that's equal to alpha itself, alpha 1. Whew. All right, so alpha 1 is in K join delta, and if there is, okay, great. So what we've shown here is we have constructed a extension where I go from K to K join delta, and we do that, we have access to the root alpha 1. So in the event that we have one root, this is, we're done because t squared minus alpha 1 squared, that's fine. That degree is less than 5. Now if we have another root, so otherwise, so if we have more than one root, then K adjoin delta gives us access to alpha 1. That's going to sit inside K2, which we're going to set to be K adjoin delta alpha 2. Okay. Now, similarly to how we've argued, adding in alpha 2 is going to define for us a homomorphism an to z mod p with p prime. Okay. So an is going to act on alpha 2, and it's going to have to send it to a pth root of alpha 2 squared, or alpha 2 to the p, right? Just like in the previous argument. This will only exist if what? Well, it only exists if n is equal to 3 or 4, and p is 3. Oops. Okay. In particular, we will not be able to come up with this homomorphism if n is 5 or more. So there's no tower of Ruffini radicals when n is bigger than or equal to 5.